So far, we've identified the edges in our image and isolated the region of interest. Now we'll make use of a technique that will detect straight lines in the image and thus identify the lane lines. This technique is known as Hough transform. We'll start by drawing a 2D coordinate space of x and y, and inside of it a straight line. We know that a straight line is represented by the equation y is equal to mx plus b. Nothing new so far, just simple math. Our straight line has two parameters, m and b. We're currently plotting it as a function of x and y, but we can also represent this line in parametric space, which we will call Hough space, as b versus m. We know the y-intercept of this line is 2, and the slope of the line is simply rise over run, the change in y over the change in x, which evaluates to 3. Given the y-intercept and slope, this entire line can be plotted as a single point in Hough space. Now imagine that instead of a line we had a single dot, located at the coordinates 12 and 2. There are many possible lines that can pass through this dot, each line with different values for m and b. You could have a line that crosses it with m and b values of 2 and 8, 3 and 6, 4 and 4, 5 and 2, 6 and 0, so on and so forth. Notice that a single point in x and y space is represented by a line in Hough space. In other words, by plotting the family of lines that goes through our point, each line with its own distinct m and b value pair, this produces an entire line of m and b value pairs in Hough space. What if we also had a point at 8 and 1? Once again, there are many lines that can cross this point, each line with different values for m and b. All of these different values for m and b represented by a line in parametric space. The point being, whenever you see a series of points, and we're told that these points are connected by some line, ask yourself this question: what is that line? As previously mentioned, there are many possible lines that can cross each point individually, each line with different slope and y-intercept values. However, there is one line that is consistent with both points. We can determine that by looking at the point of intersection in Hough space, because that point of intersection represents the m and b values of a line consistent with crossing both of our points, which in this case has slope and y-intercept of 4. Suppose there is one more point in our image space, at the point 16 and 3. This point is also represented by a line in parametric space. Each point in that line denotes different values for m and b, which once again correspond to different lines that can pass through this point. But notice that there is another intersection at the same point, which means that the line with the following slope and y-intercept 4 and 4 crosses all three of our dots. Why is this relevant? Well, this idea of identifying possible lines from a series of points is how we're going to find lines in our gradient image. Recall that the gradient image is just a series of white points which represent edges in our image space. You and I can look at the various series of points in our image and automatically assume these points belong to a line, this series of points belongs to a line, so on and so forth. But what are the lines? What are their parameters? How do we identify them? Well, take these 4 points for example in our image space, which correspond to the following Hough space. What we're going to do is first split our Hough space into a grid, each bin inside of our grid corresponding to the slope and y-intercept value of a candidate line. For example, what if I told you these points belong to a line? What is that line? Well, I can see that there's points of intersection here, there's some here, and some here as well. Well, all of these points of intersection are inside of a single bin. For every point of intersection, we're going to cast a vote inside of the bin that it belongs to. The bin with the maximum number of votes, that's going to be your line. Whatever m and b value that this bin belongs to, that's the line that we're going to draw since it was voted as the line of best fit in describing our data. Now that we know the theory of how we're going to identify lines in our gradient image, you would think to yourself, alright, enough talking, time to code. Well, not so fast. There's just one tiny problem. We still haven't taken into account vertical lines. Obviously, if you try to compute the slope of a vertical line, the change in x is 0, which ultimately will always evaluate to a slope of infinity, which is not something that we can represent in Hough space. Infinity is not really something we can work with anyway. We need a more robust representation of lines so that we don't encounter any numeric problems, because clearly this form, y is equal to mx plus b, cannot represent vertical lines. That being said, instead of expressing our line with Cartesian coordinate system parameters m and b, we'll instead express it in the polar coordinate system rho and theta, such that our line equation can be written as rho is equal to x cos theta plus y sine theta. If you're really interested in how this equation is derived, feel free to ask me in the Q&A, but the main idea is that this is still the equation of a line, but in polar coordinates. If I am to draw some line in Cartesian space, the variable rho is the perpendicular distance from the origin to that line, and theta indicates the angle of inclination of the normal line from the x-axis, which is measured in radians clockwise with respect to the positive x-axis. Let's look at some examples. Suppose I had a point with x position 5 and y is equal to 2. As you know, this is a point, and many lines can pass through this point, including a vertical line. We used to define lines passing through our points by their slope and y-intercept m and b, but now they will be defined based on rho and theta. If we want to measure the perpendicular distance from the origin to the top of the line, the angle of inclination of the normal line from the axis is simply 0, which works out to a distance of 5. Another possible line that could pass through our point is a horizontal line. The perpendicular distance from the origin to our line would correspond to an angle of 90 degrees, which in radians is pi over 2, which ultimately works out to a distance of 2. This line, therefore, is characterized by an angle theta of pi over 2 and a distance rho of 2. Just to strengthen our knowledge, another possible line is the following, whose perpendicular distance from origin to our line corresponds to an angle of 45 degrees from the positive axis. That is pi over 4 radians, which works out to a distance rho of about 4.9. The point of all this being is that previously a point in image space represented a line in Hough space, whereas now with polar coordinates for a given point, by plotting the family of lines that go through it, each line with a distinct value for theta and rho, we get a sinusoidal curve. This curve represents all of the different values for rho and theta of lines that pass through our point. This might look a bit intimidating, but the concept is the exact same, because imagine instead of 1 point, we had 10 points, which in turn results in 10 sinusoidal curves. As previously noted, if the curves of different points intersect in Hough space, then these points belong to the same line, characterized by some rho and theta value. So just like before, a line can be detected by finding the number of intersections between curves. The more curves intersecting means that the line represented by that intersection crosses more points. In our case, all 10 of our curves intersect at a single point, which means that there is a single line with some rho and theta value that crosses all 10 of our dots. We can look at a more specific example with 3 dots in our Cartesian, which represent the following sinusoidal curves. All 3 lines intersect at the same point, characterized by a theta value of 0.92 radians and perpendicular distance of about 9.66. So that's the idea. finding which line best fits our data. In our case, it's the one with the following parameters. We can also apply the concept of voting that we discussed earlier, such that our Hough space is still in the form of a grid. And obviously, this bin would have the maximum number of votes. And just like before, the bin with the maximum number of votes, that's going to be your line. Whatever theta and r value that this bin belongs to, that's the line that we draw since it was voted as the line of best fit in describing our data. Later on, when we start implementing this, we'll talk about the concept of thresholds. But for now, that is all for Hough transform. We're just trying to find the lines that best describe our points. And that's what we're going to use to find the lines that best define the edge points in our gradient image. Let's start implementing that in the next video.